Last video I ended saying that's it for 13.5. I made a mistake. That was 13.4. This is 13.5. Spiral arms are caused by density waves that sweep around the galaxy. So we say the Milky Way has spiral arms, but why? We're going to look at two explanations in this. Two main models to explaining the spiral arms of our galaxy: the density wave model and the self-propagating star formation model. Neither of these are full explanations, and a complete description of spiral arms remains a topic of active research. So just like dark matter, we're not sure which one of these is true, if even either one of these is true. They're just really good explanations. The density wave and the self-propagating star formation models. One thing we do know, the arms of the Milky Way can simply not be assemblages of stars. Otherwise, they would wind up and disappear. We see that in this picture. If all the stars started like this, and they rotated, eventually, the arms would wind up and disappear in a few 100 million years. Which means a galaxy like ours shouldn't have arms that are visible. Our galaxy has arms that are visible, therefore this is not the case. So let's look at this first model, the density wave model, or theory. According to the density wave theory, spiral arms are created by density waves that sweep around the galaxy. The gravitational field of this spiral compresses the interstellar clouds through which it passes, thereby triggering star formation, illuminating the spiral arms. This is a little weird. I think this little thing might explain it a little better. The gravitational field, gravity essentially compresses different clouds of gas, and that compression is what's moving, not necessarily the arm. We can think of it in terms of a traffic jam. I think this is a really good example. All the cars are moving this way, right? And let's say this car is slowly painting the lanes, which means these cars are going freeway speeds, but then they have to stop because this car is going like 10 miles an hour and merge. But once they get past that, they end up going freeway speeds again, right? Now, none of the cars ever stopped moving because these are perfect drivers and they were actually able to, let one car in and then this car and then one car and then this car. So no car actually ever stopped moving, but there was still a bump right here. And this bump was also moving because he's in charge of the bump and he's slowly going on. So in the same way, if we think of these as stars, this is the density wave. All the stars move, they get kind of stuck because of gravity for a bit, but once they get past this clump, the ones on this side of the wave get to keep moving as fast as they were. They think that when the stars are clumped here, if like this one explodes, it makes a bunch of gas everywhere, and this one explodes and makes a bunch of gas everywhere, then these two, the two right here that exploded, the gas will meet in the middle and form a new star. That's why the spiral arms have so much new star formation, because all the stars get clumped up in this traffic jam, explode and can create new ones, but then the wave slowly moves on. This leaves behind stars. This would also explain why most of the really bright stars, the bright blue ones, are in the arms, because that's where all the new star formation happens, and why all of the old red ones are hanging out by themselves on the freeway like this, because they were made by a wave long ago. The wave moved on, but that star is still standing there, still just burning, having a good time, waiting for the next density wave in a couple 100 million years to pass by it. Here's another more sciencey drawing that I don't think does a good explanation. So this model explains why the most hot O and B stars exist near the spiral arms, whereas the cooler stars are uniform throughout the galaxy's disk. Remember, the hotter the star is, the quicker it dies, so that's why we only see the really hot stars in the arms, in the density waves. All the other red stars are evenly spread out because you make one of them and they'll last forever. They'll last for billions of years. But the blue stars do not last for billions of years. They only last for millions of years. The galaxy were not experiencing density waves. What shape would it have? It would have no discernible arms, according to this theory. Give me 1 second. Okay, so I should label this 13.5 right here. This is talking about the second model of arm formation in the galaxy. Arm formation in the galaxy. This is the self-propagating star formation model. According to this theory, spiral arms are caused by the birth of stars. They reveal themselves as either grand design spiral galaxies or flocculent spiral galaxies. So the density wave model says density waves cause stars to form. In other words, the waves in the form of arms cause the stars to form. This model is saying the stars forming causes the arms to exist. When the stars form, they release a bunch of material, and that material gets stuck together and eventually ends up as a cloud of material traveling. Do you see like the opposites here? The first one said that the arms are forming the stars, but this one is saying that the stars are forming the arms. Here's a really cool picture of another galaxy out there somewhere. I failed to write down the name of this one, so I'm not sure what it is. Here's one where the spiral arms are flocculent. They're not as, I might be pronouncing that word wrong, but they're not as defined, right? Here you see very clear arms. You can point out that one. You can point out that one. There's even little offshoots. But here, you can tell it's a spiral, but there's no like definite, here's an arm. Maybe that's an arm, I guess. Maybe that's an arm. I don't know. If astronomers learned that the earliest galaxies in the universe were flocculent spiral galaxies, what would this suggest about which came first, stars or spiral arms? Because the arms of flocculent spiral galaxies are likely the result of star formation, this suggests that stars came before the spiral arms in the early universe. Okay, but notice it says if we learn that. We're not sure what happened first. We're just saying if we find out that the earliest galaxies were flocculent, then we know stars happened first. But we don't know that first bit, so we don't know the second stuff. Wow, that is a fast section 13.5. Let's just combine 13.6 into this. Infrared and radio observations are used to probe the galactic nucleus. So we know the first section for this week talked about dark matter, and we know that there's mass missing. The second thing we just went through talked about the arms in the galaxy themselves. How were they formed? What might they be? Are they the density wave model? Did the stars form the arms, or did the arms form the stars? We're not sure. It's one of those two models. So now let's look at the center of our galaxy. The only way we study it is through radio, infrared, and X-ray emissions, which are able to pass through interstellar dust. Remember that dust is stopping a lot of light, a lot of types of electromagnetic radiation from reaching us. So we can only use certain kinds. Only measure certain kinds, sorry. Here's a couple pictures. We see A is a wide-angled infrared view. We zoom in to get this picture, and we see the galactic center. And we zoom in even farther, and we see what we think is the center somewhere over there. We call it Sagittarius A star. That's what, hey, you read that, Sagittarius A star. We'll look at what that is in a second, but I do want to point out this is 1 light year across. You see how many stars are within 1 light year here? That is incredibly dense. The closest star to us is like 2 or 3 light years away. And here in the center of the galactic, center, we have hundreds of stars within like 2 light years of the center. That is crazy dense. Imagine being on one of these planets and seeing all of these stars so bright. Like, that would be insane. 100 really bright stars at night, like, I can't even imagine what that might look like. So when we track down all these radio, infrared, and X-ray stuff, we find a really strong radio source called Sagittarius A star in the galactic center. And based off of some things we're going to see, we know that that's a supermassive black hole with a mass of about 3.7 times 10 to the 6 solar masses. That's a lot of mass. It's a supermassive black hole. Now, a bunch of scientists have measured a lot of the stars orbiting around this black hole. One of them is going 27 million miles an hour. That is 4% of the speed of light. That is fast, okay? That is ridiculously fast. Just so you guys know, the fastest object we've ever made was 165,000 miles an hour. So think of how much faster this can go. Keep in mind, this is a star moving 4% the speed of light. Think of how massive that thing is. Think of how fast that thing has to go, how much energy that has. So that's another reason why we know it's a supermassive black hole there, because only something with an incredibly strong gravitational pull can get something as large as a star to be moving that fast. Here is a little screenshot, almost, of tracking a couple of the stars near Sagittarius A star. So we see all of the red dots are where the star was in 1995, and it follows the years until 2003, which is the purple dots. So we can see how far they went based off of like this little computer image. So how would stars around Sagittarius A star be moving if a supermassive black hole were not found there? The stars have been moving much slower. As we pointed out, there's one star over there moving 4% the speed of light. That is insane. That is crazy. That's one of the reasons why we know there is a supermassive black hole there. If it was not there, there's no reason for us to expect any star moving that fast. It just doesn't make any sense. It doesn't make any sense unless the black hole is there. Now, every once in a while, we get super bright X-ray readings from Sagittarius A star. And what that lets us know is that sometimes things can fall into it. Objects can fall into the centers of galaxies. Here we see a picture, a radio view of the galaxy and an X-ray view of the galactic center. We see that if this is Sagittarius A star, there's a bunch of hot gas up here and down here, probably from something getting sucked into Sagittarius A star, and then some of the material getting shot up and down. We've measured radio wave peaks before. Sometimes we can do the math and figure out how large the object was. In one case, something the size of Mercury fell into the black hole and pretty much got torn apart and lit up nebula around it for like 50 light years. Oh, so that might lead us to this question. Why would the brightening of a nebula near the galactic center suggest the presence of a supermassive black hole? Well, the gases in the nebula, for it to glow, need to be energized. They can be energized by X-rays being given off of the black hole, and the black hole gives off X-rays if it absorbs something. So if we follow that train of thought, that means the black hole absorbs something, the black hole gives off X-rays, the X-rays energize the nebula, and the nebula's brighten. So that's why that evidence works right there. And that's it, you guys. We made it to the very last slide in astronomy class. It's kind of crazy to think about.